Hi everybody, welcome to our introduction on vectors. We're going to start by being able to describe vectors. Homework assignment is pretty brief, not too many things. The reading is really important though. This is a lot of new material. If you're taking upper level math, you're definitely going to want to try to get as good of a foundation as you can before going into that. Our objectives here are to write the component form of the vector, perform the vector operations, and interpret the geometric results of those operations. We're going to write the vector as a linear combination of standard unit vectors, and we're going to solve some different problems. I'm going to give you at least one example of that today. We're going to start with sort of a warm-up here. So, 4 people push on a rock. Each person is pushing from a different direction with a different amount of force. Now, here's what we need to know about the vectors. In a two-dimensional system, you might have an x and y axis. In a vector system, we would have the directions that go along this. So we might call this the y-hat direction, or the x-hat direction. This little hat key, it's like Shift 6 on your keyboard. That's indicating a directional component to this. Y-hat is sometimes used more frequently though. We'll call this the j-hat direction. And in the x-axis, we'll call it the I-hat direction. So let's draw this picture. We've got a rock here. We've got 4 people pushing on this rock. So one person is pushing east with a force of 50. So east would be this way. Pushing east with a force of 50 pounds. The direction that this person is pushing is in the positive I-hat direction. So 50 pounds in the I-hat direction. The next person is pushing west with a force of 30 pounds. Now this person is pushing along the x-axis, but in the opposite direction. So they're pushing in the negative I-hat direction. One person is pushing north with a force of 35, so north would be up in this frame. And they're pushing upwards in the axis. This would be the y-hat direction or the j-hat direction. And one person pushes south, so they'll be downwards with a force of 60 pounds. Now, again, it's down, so this would be negative j-hat direction for the 60 pounds. What we're going to do is to find the resultant vector. The resultant vector is usually capital R, the resultant vector, the addition or subtraction or some combination of different vectors. So we're going to add these components together. So we have 50 pounds in the I-hat, but 30 pounds in the negative I-hat. So that would be 50 minus 30 in the I-hat direction. And then we would have 35 minus 60 in the j-hat direction. Adding these up, the total resultant is 20 I-hat. And then 35 minus 60 is negative 25 in the j-hat direction. This problem alone gives us a nice introduction to vectors. We're going to get into some of the more specifics next. There are 2 ways to name a vector, so let's draw the basic one. I'm going to have 2 points in space. I'll call this one A, and I'll call this one P. Vector is starting at A, passing through P, and it goes on forever. This might look familiar to you. This is how you would draw a ray in geometry. I would write this with the 2 letters. So this is A and P, with a little ray symbol on top. In geometry, we call this a ray. This is the same thing as a vector. So we can name it with these capital points here. We could also name it with a specific letter, frequently lowercase, sometimes uppercase, but I can name this vector here as vector R. The symbol stays the same, little arrow on top indicating that it's a vector. The arrow should always point to the right, that's just the symbol. You don't move the arrow around when you're indicating it. So capital points, A to P, this is the vector, and the A is where it starts, so it goes first, so AP, vector, or you could just call it vector R. The book gives a nice overview about the component form of the vector, talks about the difference between scalar quantities, which are just simple numerical calculations, and vector quantities, which have both magnitude, that's the scalar component, and a directional component. So force, velocity, acceleration, they always have some sort of vector component, some directional component to them. As the book points out, vectors that have the same directional and magnitude components are considered equivalent. So let's do an example of that. I have two vectors, v and u. Now you'll notice there's no symbol on here. This is a textbook convention, so they won't put the symbol, they'll just use the boldface to indicate some sort of directional component or vector component. So v is a vector, it's represented by these 2 points, 0, 0 to 3, 2. So there are horizontal and vertical components here. And we've got another vector u from 1, 2, 4, 4. The vector v would be these components. So I've got over 1, 2, 3, and up 1, 2. So there are 3 in the I-hat direction and 2 in the j-hat direction. Vector u starts at 1, 2. So from 1 it goes over 1, 2, 3, and then up 1, 2. So v and u have the same, we'll call it the same shape. Okay? We need to check to make sure the magnitude is the same. Magnitude calculation is a little bit different. You haven't seen the symbol before, but it looks like the absolute value symbol, but on both sides. So if I want to calculate the absolute magnitude, shouldn't say absolute magnitude, just say magnitude. If I'm going to calculate the magnitude of v, it's going to look like the following. It's just the distance formula. So I take the directional components, so from 0 to 3 is 3, so it's going to be the square root of 3 squared, plus, and then I take the vertical components, 1, 2, squared, and then what we get is 3 squared is 9, 2 squared is 4, so this whole thing is the square root of 13. If I do the same thing with u, u's magnitude would be calculated as the square root of, again, over 3 up 2, so it's 3 squared plus 2 squared, which is equal to the square root of 13. So what we can say here is that the magnitude of u and the magnitude of v are the same, and so in an expression we would write magnitude of u is equal to the magnitude of v. There's different ways to write vectors, and the next one is called the component form. Component form is essentially the same thing as that directional I-hat, j-hat form, except in a more compact form. So notice the difference here. I've got a point that for this vector that starts at the origin, goes from 0, 0 to v1, comma v2. This is a point with the parentheses. These arrow brackets here are the component form of the vector. So this is the same. This expression here would be the same as v vector, which is equal to v1, which is just the scalar, just a number, v1 in the I-hat direction, plus v2 in the j-hat direction. These are exactly the same. It's just a matter of notation. Some important conventions to note: if the length of a vector is equal to 1, that is called a unit vector. If the length of the vector is equal to 0, that means that v is a 0 vector. Now notice the boldface on the 0. That means that there's a direction, but the length is keeping it from going anywhere. This leads us into a discussion of vector operations. So the algebra of vectors is pretty similar to the algebra we all know. So if we had two vectors u and v, and we have some scalar c, the vector sum of u plus v is just adding the individual pieces. So these are the I hat pieces, these are the j hat pieces. Scalar multiple of c and some vector, while c times u just multiplies each of the component pieces by that same value, c. The negative of a vector is just the same as multiplying by -1, and so it follows the scalar multiplication rule for c. And so negative v is just v with the two components negated. And then we can add and subtract vectors just the same. U minus v is the same as u plus negative v. And again, I would subtract the difference from the two component forms. Geometrically, the sum of the vectors looks like this. So if I have two vectors, u and v, if I were to add u plus v, what I'm essentially doing is I'm just taking v and tacking it on to u. So I would draw v like this. And then the resultant vector, which we frequently write as r, the resultant vector is from the starting point of u to the end point of v. This is the resultant vector. I'd like to point out to you that if I start with u and add on v, I get this resultant vector. I get the same thing if I start with v and add on u. I get the same resultant vector. The position is different because I start here with u and I start here with v, but the end result is equivalent. This resultant vector is equivalent in both. Some quick vector operation practice. If I have two vectors, v and w, if I want to find the following, we do the algebra. So a, if I have 1/2 of v, that's equal to, I'm using r as the resultant, it's equal to 1/2 times each of the components. So it's 1/2 times -2, comma, 1/2 times 5. So that resultant vector for 1/2 v is equal to 1/2 times -2 is just -1, comma, 5/2. For b, if I'm subtracting the two vectors, the resultant vector here for w minus v is going to be component form. So w is 3, so it's going to be 3 minus -2, comma, and then 4 minus 5. And so the resultant vector here is going to be 3 minus -2, which is 5, comma, 4 minus 5 is -1. And for c, I can combine the algebraic properties in one step, so I have v plus and then 2 times w. So the resultant vector r here would be -2 plus 2 times 3, which would be 6, comma, 5 plus 2 times 4, which would be 8. And so our resultant vector here would be 4, comma, 13. Remember, these are not parentheses, these are the arrow brackets to indicate direction. We have the following properties of vector operations. So they're commutative, so u plus v it gives me an equivalent result as v plus u, put a resultant there. The associative property works, u plus v plus w is the same as u plus v plus w, so the order doesn't matter for addition. If I add the 0 vector to a vector, u plus 0 vector is just u. If I add the opposite direction, u plus -u, I get the 0 vector. Not just 0, notice the boldface, the 0 vector. If I multiply through c times d times u, it's equal to the same as c times d times u. C plus d times u is equal to c times u plus d times u. That's That's the distributive property. Again, more distribution. If I multiply c times u plus v, it's the same as doing c times u plus c times v. And then, kind of importantly, if I multiply 1 times some vector u, I just get u. If I multiply 0 times the vector u, I get the 0 vector. Notice the bold face. The 0 is a scalar multiplication. The vector directions still exist. So the 0 cancels out the scalar quantities, but not the directional components. A consideration that we make in terms of vectors is what is the directional unit of some vector. So if we have some vector v, which is non-zero in space, then we could write the u, and this is usually reserved, u is the unit vector. The unit vector of this thing is equal to the vector v divided by its magnitude, or frequently written as 1 over the magnitude times v. I'll give you an example of this. So if I have some vector v in space, I could break that vector v down into its components. So v would have the following. I would have some v1 component in the i hat direction, or the x hat direction, same thing. And then I would also have some component v2 along the j hat direction, or y hat direction. This would be the vector's components. This is the whole vector. I get to the endpoint, if I'm starting here, I get to this endpoint here by going this far over in the x direction and this far up in the y direction. The unit vector you can consider to be like the singular unit of space. So I want a distance of essentially 1 along this v vector. So a unit vector would be just this little piece here. This would be the unit vector. And again, the unit vector is equal to the vector itself divided by its magnitude. Now the standard unit vectors are I hat and j hat. I is essentially just 1 in the x direction. J, as the unit vector, is just 1 in the y direction. So we get the standard unit vectors. You can get a little practice writing this in component form. If I have u as a vector with an initial point of 2, -5, and a terminal point -1, 3, then I can create a unit vector by starting here and ending here. So the u vector would have the component form of starting at 2, going to -1, that's a difference of -3 in the I hat direction. Starting at -5 and ending up at +3, that's a difference of +8 in the j hat direction. And this would be our vector u. In this case, u is not the unit vector. It's kind of confusing how the book switches back and forth between those two things. If you're just making up vectors, I would suggest not using u and reserving that just for the unit vector calculations. If we've got vector v as 2i minus j, w, if you have this resultant vector as 2u minus 3v, w would be calculated as 2 times u, so -3, times 2 would be -6, and then minus 3 times v, so -3 times 2 would be -6 in I hat direction. If I then take the j hat components, w is 2u, so u was 8 here, so 2 times 8 is 16, minus 3 times v, v is -1 here, -3 times -1 is +3. And so we get this in this component form negative 6, negative 6. So we get negative 12. 16 plus 3 is 19. To write this as an equivalent vector in the I hat j hat frame, w would be equal to negative 12 I hat plus 19 j hat. To write this in the I hat and j hat frame, I read this as negative 3 I hat plus 8 j hat. These two forms are equivalent, just different ways to write it. I'm going to end this lesson with a little application of vectors. You mostly see applications of vectors in science and engineering, so force comes up frequently, especially in physics. So we're going to look at the resultant force when more than one force is acting on an object, kind of like the same problem we started with in the warm-up. Here's our problem. We've got two tugboats that are pushing on an ocean liner at an angle of 20 degrees. Each boat is exerting a force of 400 pounds. What's the resultant force on the ocean liner? So we've got some ocean liner here. Let's draw a boat shape here. I've got two tugboats in the back that are pushing on the ocean liner. Now I'm going to draw in the horizontal here. So I've got one boat pushing this way with a force of 400 pounds. I've got another boat pushing this way with a force of 400 pounds. And I want to know what's the resultant force. Now, visually, you've probably got a good idea here. This boat is pushing this way, this boat is pushing this way. Together, they're pushing along this way. Let's break this into the component forms. So this is an angle of 20 degrees here and 20 degrees here. Each of these boats can be analyzed by their components. So the first boat looks like this. It's got a force of 400 pounds. Okay, but I've got an angle of 20 degrees here. And so we can use a little trigonometry here. So what is the component of this? Because remember, this is the right angle between the horizontal and the vertical. So if this is 400, how do I calculate this? A little trigonometry is in order. So the component along the x-axis would be in terms of the cosine. Cosine is the horizontal piece here. So this term here is going to be 400 times the cosine of 20 degrees. The vertical piece is, remember from back in your trigonometry, is going to be the vertical component along this side would be, okay, so this is opposite and hypotenuse, so this would be the sine. So this component looks like 400 times the sine of 20. This boat has a similar map, but the sine is reversed, sorry, 400. The sine is reversed here, so this is also 400 times the sine of 20. This is also 400 times the cosine of 20. But here the direction is reversed, so this is going upwards, so this is in a positive j-hat direction. This one is pushing down, so this one is in the negative j-hat direction here. And so if I want to write the total resultant vector here, r is equal to, it's going to be 400 times the cosine of 20 degrees. Both of these are pushing sort of this way. And so it's 400 times the cosine of 20 plus 400 times the cosine of 20. In the I-hat direction. And then plus, in the J-hat, this vertical component is pushing downwards. This vertical component is pushing upwards. And so what I get here is 400 times sine of 20 minus 400 times sine of 20 in the j-hat direction. These two are opposite, and so they're going to cancel each other out. And so the total resultant vector is, now I can add the scalars here on the cosine terms. So 400 cosine 20 plus 400 cosine 20 is just 800 cosine 20 in the i-hat direction. And that is the resultant force. You'll notice there's no vertical component. I can write 0 j-hat. Make sure that is clearly communicated. But there's no resultant force in the up and down direction, only to the positive i-hat direction in this case. And that's the end. Good luck on the homework.